The last video in this section is just going to formalize what the last couple of videos have been building up to, but I just want to make the disclaimer pretty quickly and early on that it's not going to materialize in anything that you will feel particularly useful or earth-shattering. It's not like when in geometry we finally prove something like the Pythagorean theorem and we say to ourselves, oh, thank goodness, that gives me such a useful tool. Now I can solve every right triangle in the entire world. The second fundamental theorem doesn't really give us a lot of useful tools. It doesn't really open up a whole new world of calculus heretofore unexplored. It doesn't really allow us to solve anything in a super interesting way. It's almost kind of like the IVT and the NVT, where you end up just going, oh, okay, so that exists. And without necessarily having seen a lot of problems in context, it sort of lands like a lead balloon. Most people realize pretty early when they're doing fundamental theorem problems, it's not particularly interesting. And I know that's mathematical blasphemy, so I apologize to those of us for whom I just really shattered your dreams of something called the fundamental theorem being so revelationary. It's kind of not. Because the second fundamental theorem of calculus basically says, hey, you're going to do an antiderivative. And if you do a derivative, it's going to take you right back to where you started because you canceled its LL. That's all it says. That's basically it. It's not that different than when your elementary school teachers told you that adding and subtracting will cancel each other out, or that multiplying and dividing will cancel each other out, or when your Algebra 1 teacher taught you that square roots would cancel squares. Maybe when your Algebra 2 teacher taught you that exponentials will cancel logs. It's really just building on that idea, which is so old hat at this point that you're probably not impressed by it anymore. You know that the world of algebra is just full of opposites. The second fundamental theorem is just another layer of opposites. Now you can add that to your repertoire of algebraic opposites that you know. Adding and subtracting are opposites. Multiplying and dividing are opposites. Squares and square roots are opposites. Exponentials and logs are opposites. And now derivatives and integrals are opposites. Again, we've known that. This is not new information for us. The second fundamental theorem just formalizes what we've already intuitively understood for quite a while now, and that's why it's a bit underwhelming. It is a fundamental idea. I mean, the entire curriculum that you've learned all year is predicated on derivatives and antiderivatives being opposites of each other. That's why they're so important. But honestly, you came into calculus knowing that those two things were going to be opposites. So this is fundamental in that it sets the tone for why we're here, but it's not necessarily going to rock your world. Now that you're here and you already know that, it's just confirming what you already know. So if you want to read the second fundamental theorem of calculus in its really abstract, very formal mathematical language, you can read it here, you can highlight it here, you can memorize it if you really want to. No one is really going to ask you to ever state the second fundamental theorem of calculus because it's stating something that to you might be intuitively obvious. That if you have an integral and you take a derivative of it, you end up back where you started. The same is also true if you think about it the other way. If you have a derivative and you take the integral of it, you end up back where you started. So it doesn't matter in what order you apply those two inverse operations. The derivative is always going to cancel the integral, and the integral is always going to cancel the derivative, and the moral of the story is you always end up back at the original function you started with. The only thing worth noting, I guess, is the fact that when you do an integral and then apply an integral and then apply a derivative, your dummy variable ends up disappearing and you're back in terms of x. That was a formality that we spotted in example number 2. That's not really important. It's just something to note. Now, if you want to take more time to delve into why it's so fundamental in the big abstract picture of calculus, Google it and you're going to find tons of videos from college professors and other teachers who spend a lot more time going in the real depths of it. I personally don't, just for practical purposes and because it's not something that in a practical sense you're really tested on either in college calc or in AP. So that's my personal choice, is to not really fixate on too much of the abstract, but if you're interested, a good self-study is certainly optional. What I want to make sure we do in this last video is just to take the most practical approach possible and to remind ourselves when you have to do a problem that specifically says use the fundamental theorem, or when you specifically do a problem that looks like number 3, where you're taking a derivative of an integral, that you have a practical set of steps that you know you can use. So I'm going to do a couple of examples in question number 3. I'm going to have you do the same. And then I just want this idea to marinate a little bit, because that really is going to set the foundation for where the subsequent pages of this lesson are going to take us. And I don't think it's worthy of building too much too fast. Now in number 3, letter A, it says use the second fundamental theorem to find the derivative of each integral. By the way, I would be remiss not to just mention, now they're specifying use the second fundamental theorem. The original fundamental theorem, the OG one, was on the page 6 that we looked at the beginning of this playlist. The OG version of the fundamental theorem was, hey, you can take an antiderivative and plug in to evaluate. That's all that is. The second fundamental theorem is the one that talks about the opposites. So if you want to keep your 2 fundamental theorems straight, the original fundamental theorem, some people call it the first fundamental theorem, is the one that says that an antiderivative can be done by plugging in its limits. The second fundamental theorem is the one that says that a derivative and an integral cancel each other out. Those are the Cliff's Notes versions, of course. But they are 2 technically different ideas, which is why you'll see them referred to as the first fundamental, or the original fundamental, and the second fundamental. Just a note on vocabulary in case that's confusing you. But again, these are not formulas anybody's ever going to, or rules that anybody's ever going to ask you to explain or to specifically reference. These are not really things you need to be able to articulate. It's more just vocabulary to be familiar with, so that you know when you see a problem that says use the second fundamental, you say, oh, derivative integral, cancel each other out, got it. In fact, some people kind of look at number 3, letter A, and they just tell themselves, oh, derivative of the integral, those are going to cancel each other out. And they look at letter C and they're like, derivative of the integral, those are going to cancel each other out. And it's actually completely okay to think about that. I mean, to be honest, that is what's going to happen. If I go back and look at example number 2 from up at the top of the page, I mean, I did a lot of work only to realize that my answer was the exact same function that I started with. It's just got x instead of t. So all of this work that I did, all of this antiderivative, plug in, evaluate, then take the derivative, all that stuff, gave me the exact same freaking thing as the original f of t. In other words, the original thing that was inside of the integral in the first place, just with my new variable plugged in. Now, the reason why I'm making that observation is because I'm looking at number 3, letter A, thinking to myself, holy crap, I can't even do that. This is impossible to do. And you might be saying to yourself, oh, Herbert, gosh, is this where the other shoe is going to drop and now you're going to teach me a whole new rule of integrals that I didn't even know? No, this integral can't be done with the tools that we have. It's a chain rule, so I'd have to use a u sub, but the u would have to be t squared minus 1. The derivative of that would be 2t. I don't have a 2t anywhere in the problem. I'd be stuck. I wouldn't know how to do this. So this is why knowing the fundamental theorem is actually going to bail me out big time, because I can't even do the first step. I can't even do the integral, let alone take the derivative of an answer that I can't find. So this, again, is where the second fundamental theorem is going to come in so handy. We know that if we take that integral, we're going to get some messy answer. Still don't know what it is. I'm not even supposed to know what it is. I'm going to get some messy answer, and I'm going to take its derivative, and then I'm going to end up right back where I started. I know that I started with a function that is something squared minus 1. But I know that in the process of doing the integral and doing the doing the integral and then doing the derivative, that x is going to end up getting plugged in instead of my dummy variable t. So even though I have no idea what the actual derivative or antiderivative process looks like, I know that at the end of the day, I'm going to end up with the same exact function that I started with. And I'll highlight it so you can see where I'm referencing. The same exact little f of t, the same exact function inside of the integral in the first place, but with the dummy variable out, new variable x in, I'm going to end up with square root x squared minus 1. I just know I will. Because that's what the second fundamental theorem essentially says, that the derivative and the integral are going to cancel each other out, and what you're going to be left with, and technically the derivative is canceling the derivative here as well, what you're going to be left with is the original function just with that plug-in. That plug-in does have to happen because technically that's the part that we're skipping, that we don't really know how to do, but we should be doing. We know that we're going to have to plug in and evaluate and then take the derivative and everything's going to cancel. So I'm cutting out the middleman for sure, but I'm remembering that extra little twist that I have to replace that dummy variable with x. But if you know that's going to be the case, why would you bother doing a whole bunch of calculus? If they're giving you the actual function, we just have to realize, oh, loophole, then we can take a way easier route through these problems. We don't actually have to do the calculus at all, even if we can. I mean, I guess we could do the real calculus on letter C. The antiderivative of 1 over t is ln t, or ln absolute value t. We could plug in x, we could plug in 1, then we could do the derivative. Spoiler, we're just going to end up with 1 over x as the answer. And you might be saying, oh, Herbert, you only knew that because you're a math teacher. You only knew that because you made the answer key. Nuh-uh, here's how I knew that. The original function, f of t, was 1 over t. When I take its antiderivative, and then I take its derivative, those two operations are going to cancel each other out, and what I'm going to be left with is the exact same structure of the exact same function, just with x plugged in instead of t. So it is completely fine if you take that shortcut. It is completely fine if you don't show any work to these questions, because that's the freaking point. The whole point of the second fundamental theorem is actually to make your life a little bit easier and to say, hey, if you understand that inverse relationship, take advantage. Don't show any work. Save yourself the time. You have to take the derivative of an integral, cancel them out, replace your dummy variable, and boom, you're finished. So knowing that, it might only take you a couple of quick moments, and I say moments, not minutes, moments, to do letters B and D, because there is no real calculus involved. You couldn't even do them if you tried. I mean, B is a chain rule. We don't have a good U-sub for it. D is a product rule. We don't have a good U-sub for that either. These would be impossible to do a longer way, even if you wanted to. So see if you can apply now the second fundamental theorem in your own words or in your own thoughts and try to get your answers for B and D. Check the answer key provided on the learning plan. Make sure the idea makes sense. And once it does, I would say you've done plenty for today. Just adjusting your brain to this new reality that the second fundamental theorem